Study Unit 3, Lecture 1. This lecture focuses on resistive and inductive loads, switching mechanisms and how to characterize switching, and finishes with commutation. In power electronics, switching is used to control inductive, resistive, and capacitive loads. Examples of inductive loads are things such as electrical machines, transformers, solenoids, and relays. These types of loads, when the device is turned on, there is typically a very high rush-in of current, which is called the inrush current. This inrush current needs to be controlled in order to prevent the inrush current from damaging the equipment. An example of a capacitive load is fluorescent lighting, which also has a very high inrush current. Electromechanical loads are examples of loads which are both capacitive and inductive depending on the frequency that the load is operating at. The type of load which is being driven is closely related to the type of switching which is used. Because of this relationship, there are interrelated factors which determine what type of switching is used to handle what type of load. Examples are, well, firstly, the type of load, which is usually inductive and rarely pure resistive. There's also a switching mechanism classification, which determines how the load affects switching commutation, things such as hard switching, resonance, soft switching. And finally, the switching characteristic required to fulfill a specific VI requirement, such as bidirectional current switch or an asymmetrical sustaining voltage switch, and so on. These factors all need to be taken into consideration when deciding how the load will be switched, what type of switching will be used, so forth and so on. Two load types that will be focused on are purely resistive loads and inductive loads, although purely resistive loads are incredibly rare. The shown here is a simple switch with a simple resistive load at the collector of the transistor. The gate of the transistor is driven by a simple square wave pulse. When the gate is turned on, the transistor will start to conduct and current will be sourced through the load from Vs. To start to understand how switching can be affected by the type of load, a good place to start is to look at the collector emitter voltage of the transistor. The collector emitter voltage as a function of time is given by Vs minus the differential voltage across the load as a function of time. So in a Persian form, there's simply VCE as a function of t is equal to the supply voltage minus current through the load as a function of time multiplied by the load constant. So from this equation, it should be apparent that the collector emitter voltage will change with time as the current through the load changes with time. Shown here are four plots. The first plot is the shape of the gate voltage, which is a simple square wave. VCE is a plot of VCE versus time. The third plot is a plot of the current through the load as a function of time. And the final plot is a plot of the switching power used, also as a function of time. From the plot, it should be apparent that the transistor here is not modeled as an ideal switch, and there is some transient as the transistor starts to switch and VCE starts to change. This is also true for when the device turns off, with a similar type of characteristic curve. From the graph, as VCE decreases, in other words, as most of the voltage across the load, the current flowing through the load will also increase until it reaches a steady state. It is during this period that there are power losses in the switch as it switches from the off state to the on state, and again from the on state to the off state. On the plots of VCE are regions marked A, B, and C, and then when the device is turning off again, there are the same or similar regions C, B, and A. Shown here in figure 6.3 from the text is a graph which is called the switching trajectory of the switch. This graph shows how VCE changes versus IC throughout time. For this case, the on trajectory is very similar to the off trajectory, and again on this plot, regions A, B, and C are marked, and they correspond to A, B, and C on the VCE plot over here. So at point A, VCE is equal to Vs, which is the maximum voltage for VCE. Then as the device starts to turn on, VCE starts to decrease, but the current also increases. Eventually, it reaches point C, where the transistor is completely on and conducting through the load wholly. The key concept which needs to be taken from here is that the switching trajectory must be within the safe operating area of the device. If the switching trajectory goes outside of the safe operating area or takes very long to move through the safe operating area, then there will be heat dissipation in the device, which could possibly damage the device and cause a failure. During switching, the energy lost during switching is given by this equation over here, with W equal to the integral of VCE as a function of time multiplied by IC as a function of time integrated over the switching period. Expanding this integral to actually contain times and values from the circuit, the on energy wasted, WR on, is given by the integral from 0 to T on, which is this time period over here, multiplied by Vs times 1 minus T over Tn times the maximum current, multiplied by T divided by T on dt. Solving this integral yields 1 over 6 multiplied by the supply voltage squared divided by the load multiplied by the time it takes for the device to switch T on. This equation will express how much energy in joules was lost during the switching. Because of the symmetrical nature of the switching scenario, the energy wasted when the switch turns off again will be similar to that when the switch turns on. The amount of power used, or rather the amount of power that is lost during switching, can be determined by multiplying the energy used by the switching frequency. So that's simply this equation over here multiplied by the frequency that the switching is occurring at. In this example, the term for power Vs squared over RL has been replaced with the maximum current multiplied by the supply voltage. Thus the power which is wasted during switching is 1 over 6 multiplied by the maximum current multiplied by the supply voltage multiplied by the frequency that switching is occurring at. In practice, the slope, or rather the characteristic curve which describes this behavior, might not necessarily be easy to work with. For this reason, these types of behaviors are often linearized into more easily to use equations. It is from these linearized equations that these work and power expressions were derived from. For an inductive load, the voltage which is created over an inductor as the current changes as a function of time is given by B equals L di dt. The energy stored in the inductor is also simply half L multiplied by the maximum current through the inductor if the inductor is not in saturation. Note that these values do not actually take the supply voltage into account. What this means is that the voltage which is generated across the inductor can be much higher than the supply voltage, and this high voltage can damage devices in the circuit. Shown in this diagram 6.5 from the reference text is once again the switching transistor which switches on the load, and then there are 4 different loads. In each of these circuits, a different approach is used to try and control the voltage which develops across the load inductance. The most commonly used technique is what's called a freewheeling clamping diode. How this circuit works is that as the load is turned off, a voltage develops across this inductor. Once a voltage which develops across the inductor is high enough, this diode turns on, and instead of having a high voltage developing across the load, the excess energy is dissipated through the diode back into the source supply. In its simplest implementation, the freewheeling clamping diode does not make use of a series resistor or Zener diode over here. The purpose of the series resistor and diode over here are to control how the excess current, rather how the excess energy, decays through this diode into the source. The solution is to have a Zener clamping diode at the collector of the transistor. The idea being here is that if the voltage at the load exceeds the terminal voltage of the Zener, then current will be conducted through the device into ground and prevent the voltage across the load from exceeding Vs. There are some distinct disadvantages of using this. The first is that the Zener voltage needs to be higher than the supply voltage. Additionally, as the energy levels or power levels in this type of circuit increase, there are certain compromises that have to be made in order to make use of the Zener method. The first is that multiple Zener devices may be used in order to get the Zener voltage high enough to be larger than the source voltage. This circuit over here is an RC snubber network. The idea behind this circuit is that the RC snubber will leak energy away from the inductor when the voltage gets too high. This circuit here effectively creates a resonant network which will drain any excess energy away through the resistor and capacitor and back into the source. More technically, this RC network forms a filter which will have an overdamped response, which will dampen any voltage spikes which develop across the inductor. The final circuit over here is a soft clamping circuit. How the circuit works is that through this resistor R here, the capacitor voltage is held at least Vs. If the voltage which develops across the inductor gets too high, this diode will turn on and the AC current will drain through the diode and into ground. Shown here are the switching characteristics for the freewheeling clamping diode solution. The most apparent behavior of the circuit can be seen here on the effect on IC as the inductor is switched off. The voltage develops across the inductor, causing a current to flow. This goes above the maximum allowable current and overshoots at B. This, however, causes the diode to turn on, which immediately reins the current back down to the allowable IM. The effect on VCE is that VCE does not actually go above the source voltage. An important fact to note with this type of solution that even though this provides some form of protection from a large voltage developing over the inductor, the voltages which do develop even with protection need to be within the safe operating area of the switching device. In other words, the current which is developed here at point B still needs to be within the safe operating area for the device to prevent damage or heating. Similar to the resistive load, the energy which is used during the on and off cycles for the inductive load can be determined using linearized or rather simplified descriptions of the energy and power transfer curve during the switching cycle. The energy used in the on transition is the integral from 0 to the rise time multiplied by the source voltage multiplied by the maximum current multiplied by t divided by the rise time dt plus the integral from 0 to t4 multiplied by Vs multiplied by 1 minus t over tvf multiplied by the maximum current dt. This mouthful simplifies to this equation over here, which says that the energy used in the on cycle is a half Vs multiplied by the maximum current multiplied by the on time. A similar equation can be derived for the energy used when the transistor switches off. An important distinction that needs to be made between resistive and inductive loads is that with inductive loads, the amount of energy wasted is much higher than that for resistive loads. For resistive loads, this factor which describes the amount of energy wasted is only 1 over 6, whereas for the inductive load, it is a half. What this means is that the inductor switching will waste 3 times as much energy as switching to a resistive load. In other words, switching to an inductive load will have a much higher loss than switching to a purely resistive load. This concludes this lecture. The next lecture will have a look at switching types and commutation.